Thank you for the intro. Is my mic? Okay. So, hi, my name is Nori, and I work for Capital One, and I work for the card machine learning team at Capital One. One of the things that I like to brag about is that I can ride a unicycle, and I thought about entering the room with my unicycle, but that would have been a terrible idea, so I decided not to. What I do at Capital One in this machine learning team is I lead a team that's building the platform capabilities to further advance the machine learning agenda. At Capital One, we use machine learning for many different use cases, including fighting the fraudsters to catch them, as well as increasing customer experience as well. So today, as I was introduced, I'll be talking about how to build a GraphQL-based data gateway that enables you to onboard new backend data sources without making any code changes. But before we dive into that, you might be thinking, what does GraphQL have to do with machine learning, right? The fact of the matter is, machine learning is learning from data. And no fancy algorithm or math formula can replace lack of good data. So essentially, majority of the work that we do in machine learning is working with data to prepare quality data to feed the machine learning training exercises, as well as the execution of the models in production. So after conducting much research on the pain points that our machine learning engineers, as well as our data scientists, are experiencing in terms of finding the machine learning data inputs, what we did was to decide to build this thing called the data gateway. So this data gateway is not just a simple reverse proxy. We want it to be this really smart endpoint that unifies the retrieval of all the machine learning inputs. And it provides everything from being able to discover data, share the data that's other team might have worked on and derived, and not just serve them, but monitor them from both operational and feature characteristic point of view. And GraphQL is something that we found that can really help us. So one of the big challenges at Capital One is that we're a really big company, and there are a lot of data producers. So all these federated teams that has domain knowledge about their data produces the data and hosts their data in many different types of backends. And it could be a database, it could be microservices, a bunch of variety of interfaces. And what the GraphQL does that's really well, as you guys know, is to stitch all those data into a single schema, expose that, make that discoverable, and helps you aggregate all that data from different types of backends, so that data scientists, machine learning engineers can really focus on working with machine learning as opposed to doing data engineering. The second important design decision we made is that our data needs to be cataloged and have standardized interface. At the end of the day, it's garbage in, garbage out. So we wanted to make sure that the data that gets hooked into our gateway, it has all the qualities that we need. So therefore, what we did was to, in order to make the gateway just work, as the standardized source type, we preferred something that has a strong type or a schema. And everything, all the data that gets hooked up into the gateway needs to be registered in our enterprise registry. That includes not just the data on our data lake, but also your microservices, including your REST endpoint. And finally, the key thing that enables the scalability of specifically my team is to support this capability is to make everything configuration driven. So every time a new data source appears, we don't have to start with getting the specification of how that works and start coding away and pushing that changes to our production environment. So let's dive into what implementing a GraphQL endpoint looks like. So this is straight out of Apollo's documentation. You start, essentially what you see is a pretty simple schema here. What you start with is designing a GraphQL schema. So you see that there's a type called book with fields called title and author and a nested type called author. And what's happening on the right side is essentially wiring that schema type into the resolver implementation, right? And this is what it looks like on a Java stack. Here's an example taken from a framework called Java Kickstart for GraphQL. And it's essentially the same. You start with building the schema and creating some simple POJO that maps to your object-oriented implementation. And then you wire them with the resolver implementation. So this looks really simple, and these frameworks are great, right? But how do we make this implementation so that this is all configuration driven? The secret sauce is the schema first approach. As you saw in the two frameworks that just now, these frameworks guide you to build your schema first, and then the implementation. And what that allows us to do is create this separation and concerns in our components of the implementation into these 4 blocks, essentially. So there's a schema. There's the resolvers that helps you aggregate the data that the client is asking. There's the models that maps to the fields of the schema for the object-oriented model implementation. And then there's essentially the connectors that actually knows how to talk to the backend data source and retrieve the data. And essentially from there we can do is take that schema part and put it into something like of a relational database. And what we can then there is to do is in our implementation, we have this thing called a configuration service that is essentially the brain of our gateway. And it talks to the registry service to understand what data sources are out there, grabs its business metadata as well as technical data, metadata, along with the schema that is registered, or in REST endpoints perspective, the definition of what the REST endpoint looks like, and then convert that to fragments of GraphQL types and queries, and then have the data gateway stitch them up on the server side. So here's an example of Parquet data that could be onboarded onto a gateway directly without building any sort of GraphQL endpoint yourself. So Parquet data, as you might know, is a columnar data format. It looks like a table, and it's very popular amongst data scientists and data engineers, especially in the world of big data space. And in this case, I'm naming the type using the data source name and translating the Parquet fields as GraphQL fields, and populating the schema comments using the metadata in the configuration. And on the right is what's the output of the translation. Here's an example for REST endpoint. Capital One, we use Open API spec as the enterprise standard to register all of our REST endpoints. So we can take this specification and essentially do the same thing we just did on the Parquet. So the output here is a type called Web Analytics with the fields, also as well as the comments that has been derived from the REST documentation. And you can do the same thing with the query as well. So what we're doing here is in the metadata for the Parquet object, we know that it has partition keys and also has different fields, but we have our data producers tag which fields they want to expose as the filter key. So using this partition key and the filter key, we're creating this compound key that's exposed as the input of the query on the GraphQL side. And exposing these queries in this way helps you make sure that your queries will perform well, because it's always using the partition key and then always using the filter key that the data producers want you to use. Again, this is an example for the REST for the building the query. There's a part of the open API definition called parameters, and you can straight take that and then convert that into a GraphQL query schema fragment. But in this automation, one of the first things you might encounter as a problem is naming collision. So in GraphQL spec, there's no concept of namespacing that enforces unique names. So let's say multiple teams have similar names. There's a high chance of essentially teams creating similar names, and then you end up creating this collision. So what we do is, again, going back to the metadata that we have, and we're essentially generating this pseudo namespace. And in our case, taking the line of business, Capital, we're not just a credit card company, we're a bank, we do auto loans, we do all kinds of things, right? So line of business, in my line of business is card, so we can use that as the prefix, one of the prefix. And then for this particular call center analytics data source, it is owned by the domain servicing for the customer call center division. And then also we're using the version to create this a prefix in order to make sure that the namespacing or the types and the queries are generated with unique names. And then speaking of versioning, there's many ways to go about it. But for us, we're only versioning the types and the associated queries. We're not versioning the global, like the top level schema itself. The only thing that we're versioning is when we see a field that is either deleted, modified, or added into the new the change on the backend data source, we increment the version type to make the change transparent to all the consumers of the gateway. And one of the things that I want to call out is, as you increment the versions, you might want to essentially deprecate the old ones. And when you delete, as you delete different types, you want to be extremely careful, when you do so, because you might have consumers that are still using the old version. So things such as onboarding, the data with updated configuration information, as well as being able to monitor the activity of the usage, becomes really useful and important. And one of the really powerful things about GraphQL, obviously, is to represent your data in graph. So to take advantage of this, you want to define relationship between your types, right? And so here's an example of taking the past two types that we generated in the earlier slides. One's the card servicing call center analytics type and a tech digital web analytics types. And we are essentially embedding that into this card account type. So then a card account could be queried, and then from there you can drill down to either the call center analytics or web analytics that way. And then start building this ontology of your domain data, which can be extremely useful. So I'd like to take a moment to get a sense of the GraphQL community for a second here. How many people work with GraphQL on an everyday basis? Oh, wow, there's a lot of you. How many of you use the JavaScript stack? JavaScript? How about Java? Oh, that's decent about. How about Golang? Okay, only a few of you. Okay, so my team is essentially a JVM tech stack shop with Python. So we decided to implement ours using the Java language. And here's just an example of the library that we use. It's called GraphQL Java Kickstart. And it has this utility called type definition factory. And this enables you to essentially create a dynamic graph schema or GraphQL schema during the application runtime. So this is what we use to essentially, during the execution of the data graph or the gateway, we can dynamically take the fragments of the types and queries that we generate using the configuration translator, and then expose that into our the schema that we host. Another really cool library that we use is called BiteBuddy. So as you know, Java is a compiled language, but this library, what it does is it lets you, during the application runtime, generate this dynamic code and then inject that code into your JVM through the class loader. Even if you might think that there's no use for this, I suggest checking it out just because it's a really cool tool, and then it might spark some ideas on some new really interesting features that you might want to introduce in your Java application. And this is essentially what I use to dynamically build the models or the plain object that maps to the GraphQL fields and wire them to the resolver implementation during the application runtime. For resolver wiring, I leverage this implementation that I have called resolver factory. Essentially, it's just a typical factory pattern that returns appropriate resolver for requested query based on the user request with polymorphism. And our configuration has the necessary information, our configuration service has the necessary information to determine what resolver to return based on the request that we get. And behind the scenes of the resolvers, here are a few different tools that we use to actually get to the data and then bring back the data for the resolver to aggregate the data and then present the data. And in building any platform that's responsive and scalable, you always need a very good caching mechanism, right? So we also have this cache building technique that essentially allows us to dynamically create these key values that is optimal for supporting the quick lookup of the data that we have on the gateway. So what we essentially do is look at the type query and translate that into the key that we need. So the key could look like this, and then the value would be the full the JSON response before the filtering. And also, I forgot to mention that in terms of the caching strategies around essentially the retention policy, we obviously use the least recently used strategy, which is typically helpful for the majority of the use case. But we also do some pre-warming as some specific use cases are expecting to use certain subset of data. So there are cases where we can predict which data set will be accessed that day or that moment. So we would pre-warm those. And lastly, from infrastructure point of view, the most important thing to design, well, the most important thing is to design something that is obviously scalable and is also resilient. And in order to do this, we chose to extract out the component that we houses the configurations as its own microservice. And we treat them as the brain of the gate and try to give the best care. So all the way to the left, there's the two configuration nodes. These are very stateful microservice, and we don't want these to go down ever. So we put a lot of care and try to make sure this set of the microservices is always up and running. And then, but on the GraphQL server side, or in this diagram called the gateway number 1, 2, 3, and 4, these are stateless microservices. They can run out of memory because there's some really expensive query that was executed, or it needs to be taken down for some maintenance because we have some bug or some new features that we implement in the gateway. These gateways can go up and down, for those kind of purpose. Or if we need to scale up, up or down based on the load, we can do that as well. And all of this are containerized. And we have a Kubernetes cluster infrastructure deployed on our Amazon Web Services. And that is the thing that orchestrates the deployment and the resiliency of the containers that are running in our production. So I went through a lot of material super quickly. But here's sort of the summary of all the things that I just talked about. Thank you very much for your time, and I hope this was useful. That's it for me. Thank you.